A very good morning. In the previous lecture, we have derived the voltage and current expression in transmission line, and at the end, we find the solutions of wave equations in terms of voltage and current. The solutions of wave equation represents two waves. One wave is traveling in forward direction and another wave is traveling in backward directions. In today's class, we will discuss phase constant and attenuation constant. Since propagation constant gamma is equal to alpha plus j beta is equal to alpha plus j beta, where alpha is attenuation constant and beta is phase constant. The phase change per unit length of transmission line is the phase constant, and the phase of wave is equal to beta x, which is function of x. If you calculate the phase change over a wavelength, the phase change over a wavelength is 2 pi. With the help of these equations, we are able to calculate the phase constant, and phase constant is given by 2 pi by lambda. Gamma and therefore beta depends upon the primary constant and the operating frequencies. If you look at these expressions, the voltage expressions, the first term of this voltage represent a forward traveling wave, and this second term represent a backward traveling wave. If you look at the amplitude, or consider the amplitude of this forward traveling wave, the amplitude of forward traveling wave is v plus e to the power minus alpha x. This represents the amplitude of traveling wave in positive directions or forward wave at location x on the line, on the line, on the line. If alpha is greater than 0, if alpha is greater than 0, the amplitude of wave exponentially decreases with respect to x. Alpha is attenuation constant, and the unit of alpha is nippers per meter, or sometimes we represent alpha in dB per meters. If alpha is equal to 1 per meters, a unit amplitude voltage reduced to 1 by E times, 1 by E times over a distance of 1 meter. If you're trying to convert this value in dB, then 1 nipper, you obtained 1 nipper is equal to 8.68 dB. After that, we will evaluate the arbitrary constants. There are 4 arbitrary constants as I discussed in the previous lecture, and the arbitrary constants are v plus, v minus, I plus, and I minus. From this expression, we can say that dv by dx is equal to this one, and di upon dx is equal to this one. हम लोगों के पास voltage equations है, solutions of wave in terms of voltage and solutions of wave in terms of current. तो हम लोग क्या करेंगे, we will substitute the value of voltage and current in these expressions. यहाँ पे आप substitute कर दीजिए. तो आप इस पे substitute कर दिए. Substitute करने के बाद क्या करेंगे आप? You have to differentiate this expression with respect to x. After differentiating with respect to x, we obtained this expressions. In this expressions, two terms are involved. First term is wave traveling in positive x directions, and the second wave traveling in negative x directions. So we will uh, equate the equate these two equations. E to the power plus gamma x represent forward wave, or e to the power plus gamma represent backward wave. If you compare the coefficient of e to the power minus gamma x, then in the left hand side we have minus gamma v plus, this is equal to plus r minus r plus j omega l into I plus. Similarly, if you equate the coefficient of backward traveling wave, or e to the power plus gamma x, then this is equal to plus gamma v minus is equal to minus g plus j omega c. We know that gamma is equal to under root r plus j omega l into g plus j omega c. If you calculate ratio of voltage upon current for forward traveling wave, then this is equal to r plus j omega l upon gamma. Substitute the value of gamma, we will obtain, and this v ratio of v plus upon I plus, this is equal to z0, and this is the characteristic impedance of transmission line. This is equal to under root r plus j omega l divided by g plus j omega c. Similarly, if you calculate v minus upon v plus, this will also give you the same characteristics impedance. This is equal to this one. But in this case, we obtained a negative sign. Impedance तो हम लोग negative नहीं देखे आप अभी तक. So what is the significance of this negative signs? This negative sign represent the directions of wave propagations, or we will give you information about directions of wave propagations. If characteristic impedance of line is positive, then the wave is traveling in forward directions. If the characteristic impedance of line is negative, then the wave is traveling in backward directions. Or since it has the ratio, it has the dimensions of impedance, and it is the ratio of voltage and current. So this expression is called characteristic impedance of transmission line. This Z0 is a function of primary constants and the operating frequency. This is the parameters of line, characteristics of line. The characteristic impedance of transmission line is given by Z0 is equal to R plus J omega L divided by G plus J omega C under. This gamma 0, gamma propagation constant, and Z0 are the secondary constant of transmission line. The ratio of voltage and current for forward traveling wave at every point on the line is constant, and this is equal to characteristic impedance of transmission line. Similarly, for backward traveling wave, or the wave which is traveling in minus x directions, always seems an impedance which is equal to minus z0. So here z minus z0 does not represent a negative resistance in conventional sense, but rather a manifestations of directions of wave travel. Means the negative sign of characteristic impedance will give you information about directions of wave propagations, or in which directions wave is propagating. After getting this, we are trying to find the relation between the arbitrary constants. With the help of this equations, v plus upon I plus is equal to z0, and v minus upon I minus is equal to z0. V minus upon I minus is equal to z0. We have eliminated two constants, and the remaining constants is v plus and v minus. In the next class, we eliminate one more arbitrary constants with the help of voltage standing wave ratio. Thank you.